So, as you can see from the name of this lesson, we're going to be looking at solving quadratic equations by completing a square at some point. And essentially, until now, we've looked at two ways of solving a quadratic equation. One was graphically, which, if you have graphing technology, can give you an answer always really quickly, as long as you remember the idea that you're essentially solving a system where you're graphing the left side of the equation, the right side, and seeing where the two functions intersect. But we can't always rely on that. And so last time we looked at an idea that wasn't new, as just explored it in more detail, which was solving a quadratic function by factoring. Now, an important question is, well, what if you can't factor a polynomial? That doesn't mean there's no solutions. It just means you can't factor it, and so it's not going to be as quick to get to a solution algebraically. But just because you can't factor something doesn't mean there's no solutions. And so what if you can't factor something? Well, if you can't factor a quadratic expression, like I said, it doesn't mean there's no solutions, but you can perhaps solve it by completing a square. And that's why we kind of need to learn more than just factoring, because not everything has nice, clean factors. So before I get into completing the square, let's look at this expression here, or this equation here. Now, you can factor this. You could factor the left side, and it's a difference of squares. And so I can see already, if I was to solve this by factoring, even though, again, I'm going to erase this in a moment, I get x minus 3, x plus 3. I can see the solutions here are plus or minus 3. So I know those are my solutions. However, because there was no x term, it was just an x squared, but there was no x term, I could actually solve this a little more directly. I could solve this algebraically without factoring and without completing the square yet. If I just add 9 to both sides, I get a nice simple equation, x squared equals 9. And if I imagine that I'm squaring both sides, although again, you probably can just see the answer by looking at it, that means x equals a square root of 9, which is 3. Or the negative, because again, if you look at this statement right here, I don't need a square root to know that if x is negative 3 times negative 3 is also positive 9. And so as soon as I get to this step, as soon as I go from here to here, I got to realize if x squared equals a positive number, then there's going to be two solutions, a positive and a negative. Now, which of what was easier is a matter of opinion. In some ways, and actually in many ways, I like the factoring better because it made it really clear there were two solutions, positive and negative 3, which is really easy to miss when you go from this step to this step. But that's it. This also wasn't much. Okay, so before I go on, keep in mind, anytime you're solving any equation like this, where you have something squared equaling a positive number, there's always going to be two solutions, a positive and a negative. And it's really easy to forget about the negative one. With that said, what if I have something like this? Well, one option, which I'm not going to do, is to expand and simplify this, collect like terms, and then see if you can factor it. But again, what if you can't factor it? Well, and even if you can factor it, I already have it in a form that I can actually solve quite nicely without having to expand and simplify and collect like terms and then factor. Like before, I'm going to just add the constant to both sides. And so I have x minus 1 all squared on one side and 49 on the other. Like before, I'm going to square root both sides. And on the right-hand side, I have the square root of 49 is 7. But I also realize, like I said, any time you have something squared, and you have a positive equaling some positive number, there's always two possibilities, the positive, 7, or the negative. On the left-hand side, all I have is x minus 1. And that seems strange, just kind of compare it to what I have up here. Again, x squared, x, and again, it's really obvious, I hope by looking at this, that negative 3 squared is also 9. And for the exact same reason, I have to realize there's also the negative possibility here. With that said, I'm not done, but sure close. I just got to add 1 to both sides. And so if I stop here, it's kind of silly. X equals 1 plus or minus 7. That's not wrong, but if we stop here, it looks like we don't really know what this means. This literally means x equals 1 plus 7, which is 8, or x equals 1 minus 7, which is negative 6. There's my answer. So we really shouldn't stop at 1 plus or minus 7. Now, with that said, because I got answers that were nice, clean, rational numbers, that means I know that if I did expand the original expression on the left, collect like terms, and factor it, I would have been able to do that. I would have been able to factor it. But again, I've said it several times, you can't always expect to be able to factor something. For example, this equation here, the left side does not factor. There are no two integers that multiply to negative 21 and add to 10. But that doesn't mean there's no solutions. This does have solutions. If you were to graph this, I'll solve this graphically. If you were to go to Desmos and graph the left-hand side, it would cross the y-axis in two places. So there are solutions, but we can't factor it. So how can we solve it without graphing? Well, we can solve it by completing the square. So first, I want to just basically ignore the right-hand side of the equation. In fact, I even want to ignore the minus 21. I want to just focus on x squared plus 10x. And I want to, as we did in the last chapter, I want to give myself some space. And I want to create a perfect square right here. And as we've seen with completing the square, sometimes it's really, really quick. Sometimes it's not. But quite often it's really, really quick. I can just see already that to make a perfect square, I have to take 10, divide it by 2 to get 5, and square it. I get 25. So if I add 25 there, I have a perfect square highlighted in blue, which means I need to subtract 25 right beside it. And so everything you see in blue is a perfect square, which means it's equivalent to just x plus 5 all squared minus 46 equals 0. Once I get to this step, notice how similar it is to what I had right here. Same form. And so I'm going to add 46 to both sides. Get x plus 5 squared equals 46. Square root both sides. So I get x plus 5 equals, now 46 is not a perfect square. So I'll put root 46, but plus or minus. And then subtract 5 from both sides. So x equals negative 5 plus or minus the square root of 46. Now that right there is a great way to answer a question. In fact, these are what we call, this is the exact solution. 46 is not a perfect square. So if I decimalize this, it is an approximation. And so this is the exact solution. It's two answers, negative 5 plus root 46, negative 5 minus root 46. But I can't get more exact than that. However, I do appreciate it's hard to visualize, especially like on a number line where negative 5 plus root 46 is. And so if you decimalize this, if you go to your calculator and type in negative 5 plus the square root of 46, and type in negative 5 minus the square root of 46, those decimals you see are approximations. And so when you go negative 5 plus root 46, you get about 1.78. When you go negative 5 minus root 46, you get about negative 11.78. But those are, please realize, those are approximations. I'm not saying they're bad, but they're not exact, no matter how many decimals you keep. And that's because 46 is not a perfect square. So these are my two different ways of writing my answer. Mathematically, the first ones are better. They're exact. In terms of using them, the second answers are probably easier to get a sense about what they represent. OK, so notice in this case, that actually wasn't a lot of work. I couldn't factor it, but there definitely were solutions. And if I went to Desmos and graphed this, I would see those two decimal approximations. And so, as it says right here, any quadratic equation, there's no exception to this, any quadratic equation can be solved by completing the square. If an equation can be solved, you can solve it by completing the square. And so, hence the importance of this. Literally any quadratic equation can be solved by completing the square. However, in reality, there are a few examples in which completing the square is a little bit cumbersome, and we will see that. But any quadratic equation can be solved this way. So let's look at this. It's a quadratic equation. We can solve it. And so although I could leave it as it is, I could factor out 1/2 from the first two terms. I highly recommend against that because I think it's easier just to, before we decide to complete the square, let's just multiply everything by 2. We saw this last day. Again, I have an equation, and so I can multiply both sides of an equation by a number, and if I want. In this case, I definitely want to because I get just x squared plus 6x minus 12 equals 0. It's a different equation that's equivalent, that is significantly nicer in my mind. Now, can I factor it? No. There are no two integers that multiply to negative 12 but add to 6. But I can complete the square. So again, give myself a bit of space. Negative 12, no offense, I don't care about it right now. Let's make a perfect square right here. I can see to make it a perfect square, there must be a 9, half of 6 squared, which means I've got to subtract 9. Which means everything you see highlighted in blue must be the same as x plus 3 all squared. minus 21 equals 0. And now I have it in a form that I can solve in like a couple of steps. Add 21 to both sides. Square root both sides. Keep in mind, 21 again is not a perfect square. Now I will say if 21 was a perfect square, or if my number here was actually a perfect square, let's say it was 25, then that tells me, not that I made a mistake, that tells me that I actually could have factored this earlier on. Or maybe I made a mistake. But if you ever get a perfect square at this step, that just means, you know what, you actually could have factored it, which would have been less work. Factoring is the most efficient way to solve a quadratic equation, if you can factor it. But again, 21 is not a perfect square. But don't forget, as soon as I go from this step to this step, there are two possibilities, the positive and the negative. So plus or minus, really easy to forget that. And then subtract 3 from both sides. So x equals minus 3 plus or minus root 21. And again, that's my exact answer. I can decimalize it if I want, but I don't want to, so I'm done. And again, notice, as complex as it may have looked at first, you know, especially once I multiplied both sides by 2, everything came together quite nicely. And again, I couldn't factor it, but I have solutions. In fact, I have the exact solutions. Even if I use Desmos or some graphing device to solve this by graphing, I wouldn't get those exact values. I would get a decimal approximation most likely. So I did say, though, sometimes completing the square, solving an equation by completing the square becomes quite cumbersome, like this. Now, for this one, I actually don't recommend you write this down. Or, I mean, you could, but it's honestly, this is the whole purpose of this last final problem, is to show you how, even though I can solve this by completing the square, it's going to be cumbersome. It's no different than things we've done before. But this is really an example of an equation that it does not factor. It has solutions. But if I had a choice, I would actually approach this in a different way. But a way I haven't taught you yet, which is why there's one more lesson in this chapter. There's one more approach we need to learn about, especially for something like this. So how do I know this is going to be cumbersome by completing the square? Well, there's a negative 2 in the front, which means I've got to factor out negative 2 from these two terms. And right away, if I do that, I have a fraction for my x term. And then I got to take that fraction, and I got to chop it in half, and I got to square it, and I got to do all these operations with a fraction from the start. And as soon as I'm dealing with something that's not an integer from the start, it's going to quickly just get cumbersome. We can do it, but it's kind of annoying. Okay, but we can do it. All right. So the first thing I would do again is give myself some space, factor out the negative 2 from just the first two terms. So I get x squared plus negative 3 divided by negative 2 is a positive, and just 3 over 2. I could put 1.5, but 3 over 2 is exact. And while 1.5 is exact, I should say actually 3 over 2 I meant to say is just faster, I think. That's it. To give myself some space to make that perfect square, put a little plus 7 over here. OK, so now I need to create a perfect square. Whatever goes here has to be half of 3 over 2, which is if I divide by 2, that's the same as multiplying by a half. Right? Division by 2, same as multiplying by half, and vice versa, which is the same as 3/4. And then I got to square 3/4, which is 9/16. So plus 9/16. OK, now however, I got to balance things out. So over here, I got to balance out the change. Now that I did put plus 9/16, but it is being multiplied by negative 2. So I have negative 2 times 9/16 is negative 18/16. Or if I reduce that, negative 9/8. So keep in mind, negative 9/8 is how I changed my function. Negative 9/8 is what 9/16 times negative 2 is. I need the opposite of that. So I need to add 9/8 right here. OK, notice already that the sort of step I just did is so much faster when I'm just dealing with integers. OK, so now I can factor the part that's highlighted in blue. So negative 2. If I factor what's highlighted in blue, it's going to be x plus half of 3/2, which I already said is 3/4. 9/8 plus 7 whole. I need to find a common denominator. It's not that big of a deal. Make that an 8. Make that 56. Add 9 and 56. You get 65. So plus 65 over 8 equals 0. Oh, over, yeah, 8. So with that said, Let's subtract 65 over 8 from both sides. Let's divide both sides by -2. Now again, the left-hand side's fairly nice, but on the right-hand side, division by 2, same as multiplying by 1/2. And so, again, dividing by 2, same as multiplying by 1/2, which is -65 over 16. Oh, sorry, I'm dividing by -2, though. So that negative will cancel out, so it'll be positive 65 over 16. Now I want to square root both sides. So on the left-hand side, I have x plus 3/4. On the right-hand side, I have plus or minus the square root of 65 over the square root of 16. But the square root of 16 is a perfect square, so I'm going to write that as just 4 whole. And then I want to subtract 3/4 from both sides to solve for x. So I get -3/4 plus or minus root 65 over 4. That's it. They have a common denominator already, so I might as well put them together. X equals -3 plus or minus the square root of 65 over 4. Whew, and I'm done. All right, but again, while there's technically nothing there that was new, that was annoying. That was cumbersome. I got the answer. That is the exact answer. And if you graph -2x² minus 3x plus 7 into Desmos, find the x-intercepts, you will get the decimal approximations of that. But if I had a choice, I would actually not approach this equation this way. Because as soon as I noticed, and I could tell from the very first step that completing the square is going to be annoying, because taking out that factor of -2 right away led to that coefficient of 3/2 for x, and I know I have to chop that in half, I know I have to square it, I know I have to balance all these things out. I would actually use the quadratic formula for this. Now the quadratic formula is the next lesson. It's the last lesson in this chapter. And the quadratic formula also can be used on any quadratic equation. But sometimes it is needlessly time-consuming. Sometimes it is better than this. For example, for an equation like this is a great candidate for the quadratic formula, which would give you the exact same answer in the end, in less work. Not a ton less work, but less work. Whereas questions like this, I would use completing the square, because that was not actually that much. And in other cases, again, especially like this here, completing the square was really quite quick. But with that said, the quadratic formula we'll get to shortly. But most of the things we looked at, completing the square is rather efficient. But it's not always the best option.